Hello friends, welcome to Truth of Physics. Today in this particular video, I will discuss and derive all the necessary expressions and the expression of wave function, all the things in detail of the potential step or what we call the step potential in quantum mechanics. So what is it? Basically, coming to the main point, this is a graph of the potential step. What is displayed that here in the negative x direction, negative x, there is no boundary or there is no potential. This is the potential. Okay, restrictions. Potential means restrictions to any particle. Suppose we have a particle, suppose electron. So here in this region, in the negative x-axis, from the origin to the negative infinity, there is no restrictions on the particle, so the particle behaves as a free particle in this region. But in this region there is a restriction, there is a potential, and the potential, the value of the potential is v naught. Suppose this height is v naught, so there is a potential in this region, so the electron is not free in this region. So what will be the wave function in this region and in this region? In two cases, so two separate cases. What are the cases? There are two cases. Case number one is like this, that E, our energy is greater than V naught. That is the particle's energy. Suppose the particle's energy is greater than V naught, like this. Suppose the particle energy is like this. So here you can see that this is the particle energy E, and which is greater than this V naught. So what will be that case? And there are another case, there will be the case number 2, and that is E is less than V naught. So first I am discussing the E is greater than V naught. Okay, so in this case we have to find the psi 1 and psi 2. Why? Because to understand all the properties of potential step, all the behaviors of the particles in this potential step, so what it is actually meaning. Okay, so actually there are, if we think it of a classical potential step, then what happens? This is a boundary one, a wall, and suppose ball is throwing a ball. We have a ball, and this ball is, I am throwing this ball. So if the ball's height is less than v naught, then it will basically be reflected from this wall. And if the ball's height is suppose greater than this v naught, then it will definitely overcome this, and this will just pass in the positive x direction. This what happens? This happens in classical mechanics, but in quantum mechanics this will not be happening. Okay, so how this will happen, and what will be the scenarios in quantum mechanics, that we can easily understand using the Schrodinger's wave equation. So solving the Schrodinger's wave equation, we will find the psi 1 and psi 2, and after we get the values of psi 1 and psi 2 for this particle configuration, then we can easily find that how much of the particle, now it is not a particle, you will later understand that this will behave as a wave. So how much this wave, as we are dealing with quantum mechanics, so this is not a particle right now, this will associate a wave, and the wave will reflect from here, and some parts will transmit here. All the things, all the necessary things, you will get, all the necessary information you will get from the Schrodinger's wave equation, that is from the wave function. So that is the importance of why we are trying to find the wave function between these two regions, because this is the only necessary thing, the wave function, that can describe the total system, that can describe everything of the total system. So Schrodinger's wave equation is like this: H psi is equals to E psi. Okay, so E is what? The energy eigenvalue is called the energy eigenvalue or the energy, and H is what? H is the Hamiltonian. Okay, Hamiltonian means what? I think you have learned it in classical mechanics. Hamiltonian means the total energy of that system. Hamiltonian means the total energy of the system means potential energy plus kinetic energy. Now the kinetic energy in quantum mechanics is represented with operators. All the physical things, all the physical quantities in quantum mechanics, like the kinetic energy, the momentum, all the things, the position, all the things that are physically available, the physical quantities, these are called the physical quantities. These are expressed with operators. There is a corresponding operators in quantum mechanics. So, and we deal with the operators in quantum mechanics. So kinetic energy operator in quantum mechanics is like this: minus h square over 2m d2 over dx square. This is the operator. So when this will operate on this wave function, this will simply give us minus h square over 2m d2 psi over dx square plus this is what the kinetic energy now becomes. This becomes now the kinetic energy plus the potential energy. So if we deal with first for region 1, this is suppose region 1. Okay, this is region 1, this is region 2. So for first region 1, what happened? For region 1, the potential is 0 simply. So this will be 0, the potential energy is 0. Okay, is equals to E psi. We don't know what is the value of E. So solving this equation, we'll get that solution, the differential solution of this second order differential equation will be a e to the power I kx plus a e to the power I k1x plus b e to the power minus I k2x. A and b are constants, and k1 sorry, this will be 1, this will be 1, k1x. K1 means the wave number of this region. K1 means simply root over 2me over h square. Okay, okay. Now, so this is what, this is the wait a minute, this is the wave function in region 1. Mind it, this is the wave function in region 1. So this is denoted with a psi 1. Region 2, let us understand for region 2. Okay, so remind this picture. Okay, now in region 2, h star equal to E psi, this will again this do this. So h star will be minus h square plus v of x. Here v is equals to v naught x in the region 2, all over the region 2 up to infinity, positive infinity. The potential is v naught, so v naught x is equals to E psi. So this will be like this. Okay, now so the psi 2, equating this, we'll get the psi 2 is equals to, suppose c, the another constant c, e to the power I k2x plus d e to the power minus I k2x, where k2 is what the wave function, wave number in the second region, region 2, and this k2 is simply nothing but 2m e minus v naught, e minus v naught. Here e minus v naught is a positive quantity, as e is greater than v naught. We are dealing with this case, that case number 1. In case number 1, e is greater than v naught, so e is greater than v naught. Okay, so 2m e minus v naught divided by a square. So this will happen, this will be the wave function for region 2. Now a very interesting thing here, you can understand that for region 1, for this region, as there is a boundary, this is the boundary wall, this is a boundary wall, as in this region of space the particle is free, but here is a boundary wall at this point. So from the boundary wall, it is very easy that this wave will reflect. From physical concepts, it will reflect. Okay, so there is, as there is a boundary wall, there will be two type of wave function. One is the incident wave function, and another is the reflected wave function, reflected wave. Okay, but in region 2, this will transmit, suppose this will transmit, this wave will transmit. So if this will transmit, so all over in positive x direction, as there is no boundary, as the potential will be fixed throughout this positive x direction, throughout this positive region up to infinity, so there will be no chance of reflectance, there will be no chance of reflected wave. All the waves will go just in the positive x direction. So there will be not any term like this, as this represents nothing but the component or the wave in the negative x direction. So this term will vanish for the region 2, but in region 1, what happens? But in region 1, this thing will retain. Okay, actual wave function of region 2 will be like this. This will all be cancelled and the actual wave function will be like this. Okay. Okay. Now we'll try to solve the probability current density for region for the incident wave, the reflected wave, and for the transmitted wave. Means the what is the probability current density? Now we have a question. What is the probability current density, which is denoted with J vector? Probability current density is the measurement of the flux in quantum mechanics. Okay, the measurement of flux, that how much of the wave is passing through any given area, like the electric flux. Okay, so this is it's 2m. Psi star means the conjugate. Okay, as the psi can be complex, so the conjugate psi star del. This is the equation. So what will be it for J incident? For incident wave, what will be this? So for incident wave, you can easily understand that the only component will be J a e to the power I k1 x. This will be the incident wave. Okay, the wave function of the incident wave will be just this. So to find this for J, we have to find the J psi star and this thing. So I am first finding this. So psi star sin star is equals to a e to the power minus I k1 x. Okay, so we are ready to find this. So psi star into this means this into this, right? This into this. So what will be that if we do this? So this will be a square, this will be a square, or I can write mod of a square as why I'm writing this mod of a square, because when you start this, actually when you start this a can be a star, because if this constant becomes a complex number, then when you complex conjugate it, then it will be a star. So that's why a star into a is nothing but mod of a square. So I'm writing this. Okay, and this will be just a star. So mod of a square I k1 and these two things will be just cancelled out. Okay, so this is fine. Now this term minus this term psi into this means this will be minus I k1 this thing. Okay, and this is mod of a square, and this thing will just be cancelled out. So this will be the actual result, and outside it minus I squared over 2. Now, so what will be this? This will be just be equals to. Similarly, we can find the expression of J reflectance and J reflected and J transmitted. So I am just writing down the expressions. You can calculate it with your own side. Now these are the expressions of the J reflected and J transmittance. Okay. Now if we divide J incidence divided by J reflectance, then what happens? Then we will get A square divided by mod of B square, and this is called the reflectance. Which is very much important. And the another thing, J incident divided by J transmittance, if we do this, then we will get K1 called the transmittance. For the case E less than V naught, what will happen for E less than V naught? Okay, this was a potential step, and now E, this is the E is less than our V naught. This is V naught, this is V naught, this is V, this is X. Okay, so E is less than V naught, then what happens? So again, using the Schrodinger's wave equation, d2 psi over dx square plus, and for the case for the region 1, this is region 1, region 2. For region 1, the thing will be just similar. So I am not doing that thing. The thing will be just similar with the first case, and I am just writing the equation or writing the solution. Okay, and the solution will be just the same. Psi1 is equals to a to the power I k1x plus b e to the power minus I k2x. As here in region 1, so what is it, why it is happening? As region 1 there is no restriction, there is no potential, so the thing will be just same. But in region 2 something will be different. What will be different in region 2? For region 2, minus a square over 2m d2 psi over dx square plus v naught x is equals to ex, but remind that e is less than v naught here. So this will become like this, but this will not be happen because e is less than v naught. So here this term will basically be a negative term. So I can write here d2 psi over dx square minus 2m v naught minus x over h cut square x is equals to 0, because now here this term is a positive term. So here k2 is equals to root over 2m v naught minus, sorry, this will not be x, this will be our e, right, e v naught minus e over h cut square, right? Done a mistake or something, typing error, you can say here this will not be x, this all will be psi, right? This will be psi, this will be psi, and this will be psi. So if we want to solve this differential equation, that will be very much easy. M square will be equals to m square, and if we take this to this side, right hand side, then it will be just be equals to our m square equals to k2 into, okay, m square will be equals to k2. So from there the value of m will be just with the plus minus square root of k2. So here the solution will be psi2 is equals to a v e to the power minus k2x, right? So okay, this will be the equation, this will be the solution of the Schrödinger's equation for region 2. Now what is the value of j? Let us do this. J transmittance, suppose we will find the j transmittance. So then what happens, you can easily understand that as here psi2 is what a real thing, right? K2 is not a here, this is, there is no I term, right? There is no I term. So this is a purely a real number. Okay, so as this is a real number, so psi2 star will be just be equals to psi2, right? So this will be just a psi2 del psi2 del x minus psi2 this del psi2 del x. So you can easily understand that this total term will be vanished and this will be equals to 0. So j transmittance is equals to 0 for this case. So whenever the e is less than v naught, in this case always remind that the transmittance, j transmittance is equals to 0 here, means the flux, okay, the wave, the flux will be 0 at this, in this boundary. So some wave will go in this region and some will go in this region, but the total flux, the j transmittance, will be 0 here. Now there is a very important and very conceptual thing here, that if you draw the probability, okay, the probability density, that is the probability of finding the particle or the finding the wave in this region 2, then there will be some probability like this, there will be a decaying term in the probability, but here j is present here, sorry, here j is equals to 0, but why there is a probability, why we can find some wave in this region as the j is comes out to be 0, but still we can find the wave in this region. So this is a very important thing, so that I have discussed in a very detailed manner, and not only that but also the physical significance of the potential step in a very deep manner. The link of the video I will give in the description box, and subscribe this channel and hit the bell icon to get the notifications. So take care of yourself. Thanks for watching.